Okay, so let's see if, so you should see a screen, a white screen, do you? Do you see the screen?
Yes.
Okay, so that's our board. So this course is called, well, I use one name, not two, and I use historical name, statistical field theory. What is this course about? What is needed to understand this course, first of all? Well, this course is about mostly theoretical tools to understand complex systems. So, theory of complex systems. Now, what does complex system mean? Well, if you use Wikipedia to find out what is a complex system, you'll find a definition. If you Google it, you find quite a few definitions, and not every definition is consistent with another. So we will use a working definition, something we provide. We agree that for us, a complex system is the following, and who cares what the other think, okay? So for us, first of all, a complex system is a many-body system, many degrees of freedom. But these degrees of freedom must have an important property. They must be non-perturbatively interacting. So what does non-perturbative mean? Well, for those of you who have a background in quantum mechanics, a strong background in non-perturbation theory, it means that they are such that you cannot apply perturbation theory. But more generally, perturbative means interactions in these complex systems do not provide a small correction. Now, you might think of a perturbative system like an electron traveling by itself through space and traveling a little bit close to a proton and getting a little bit of a kink by a proton and keeping its own way. Now, it turns out you can compute the effect of this quick interaction with a proton, and you can do that by a technique called perturbation theory that some of you know. But in general, for us, simply seems, I don't care if you don't remember it or if you haven't seen it. What I mean is interactions are essential. They shape the core of the problem. Potrebbe essere per me, Lidia, l'ultima cosa. You have to give me, please, give me a couple of seconds. I have to collect something downstairs. So I guess we'll do the 5 minutes break now, okay? Hello?
Okay, great.
Okay. I'll be back in a moment. Okay, I apologize for this, but we are living in the era of smart working, and two parents are smart working, and they ring at the door. Then we need to take care of it. So I was discussing by sharing the screen. So I was sharing the screen, so I guess you should see this. We were discussing what we mean by complex system, and basically we were saying the concept of many-body physics, many-body systems made by many variables that are mutually interacting, such that the interactions really shape the properties of the physical system. And what do we mean by that? That in no way you can try to understand this system as a sum. So a complex system is something that is not a sum of individual components.
I'm sorry, I can't see the screen.
You can't see the screen. Fantastic. Share screen. Okay. So can you now?
Yes.
Okay. So in particular, let me give you an example of complex system that is quite prominent. Us, life, living organisms are complex systems. We are made of atoms. but in no way the properties of a living organism is in any way deducible from the sum of non-interacting carbon, hydrogen, oxygen, nitrogen atoms. Life is an emergent collective excitation from the point of view of physics, a non-equilibrium collective excitation of a many-body system completely driven by interaction. The ground state would be powder. That's what the ground state is, essentially. Look at Mars. That's very close to the ground state of what the Earth would be, right? So we are in a collective excitation, and there is no way that say a cell, but even a protein can be understood as a sum of individual weakly or non-interacting components. So when you have complex systems, all sorts of weird phenomena take place. You have phase transitions, you have collective dynamics, you have stochastic behavior, you have chaos, you have all sorts of things. So complex system is really where physics gets complicated, but also fascinating, and phenomenology gets very rich. So the real goal of this course is equip the students with tools and methods to be able to tackle complexity from a physical modeling point of view. And we will do so by combining tools. And I'm going to list a number of tools that are really mathematical weapons we are using. That's a bad word to be used for science, but it gives the idea. The focus of our study should not be on the methods by themselves, on the mathematics by themselves, by itself, but on the use of such methods in the perspective of understanding physical systems. So that's how I'd like to, we will dig into math pretty heavily at some point, but it will be always in the perspective of using that math for understanding something. So the tools that will come across quite often and represent the two main cardinal direction, X, Y, through which this course will go are two. Renormalization group and path integrals. These are the two common denominator. Of course, I don't expect these words to mean much to you at this level. And there will be additional ideas that we'll bring into occasionally, for instance, the idea of stochastic dynamic. So stochastic behavior or stochastic dynamics. And the idea of fields and field theory. But I would say these two will emerge in a couple of parts in the course, not throughout the course, while these two concepts or tools will be ubiquitous in this course and really are the main addition I'd like to provide your understanding of theoretical physics with. And today, I will begin talking about the renormalization group as first step into this course. Okay. Of course, anytime feel free to stop me, ask me, and do questions. So what is the renormalization group at all? Renormalization group, so let me start by now the concept of renormalization group came into theoretical physics relatively late in history. So roughly speaking, I guess the Nobel Prize to Wilson for his approach to renormalization group, I guess, is 1968. But I think it's in the 60s. It came to physics with rock and roll, basically. And it is as important to physics as rock and roll is for modern music. Because it basically, the concept of renormalization group is more than a mathematical aspect, is more like how you actually picture physical modeling, how you make sense of physical modeling and how you make sense to the concept of resolution of a physical theory. Not solution, resolution power of a physical theory. So it's quite interesting. Renormalization group was introduced as a mere mathematical trick to remove very dangerous infinities in relativistic quantum mechanics. You know, we're doing calculations and you were bumping into these infinities. And people, for a very long time indeed, for 30 years or so, first of all, regarded as renormalization group as a mathematical trick. And in many physics books on relativistic quantum mechanics, it is still narrated, it is still exposed as a mathematical trick. Only in the 90s, people really began to realize how deep the implication and how far-reaching they were of the concepts and how much they extended to all branches of physics, not just relativistic quantum mechanics, to the point that there is a very physical meaning to what was done in those calculations that is completely understandable even in the simplest possible mathematical terms or in simplest possible problems. Likewise, like I said before, the dipole expansion, the multiple expansion of electrostatics is a form of renormalization group, as I will show you. So the renormalization group, more than a mathematical process, is really a conceptual. And this is really where I would like you to sort of open a corner of your mind, because ultimately what this will do will hopefully teach you, will provide an answer to a question that we never formulate explicitly, we give for granted, but now it comes the time to really address and put up. And the question to which the renormalization group theory provides an answer to is the following. What does it mean to build a theory or slash a model, depending how you want to call it, for a physical process? So, as you can say, it's a pretty relevant, broad, and bloody fundamental question. It looks almost a joke. So something as fundamental as asking yourself, what is a physical theory, is almost synonymous to the concept of renormalization group. Yet, the renormalization group came to life only recently. That's the first mysterious fact. And I would like, and I'm deliberately leaving this as obscure at the moment because I'm enjoying you discovering this a little bit by little bit as I speak. I will not provide you direct answer in this course all the time. That's my style. Sometimes I generate on purpose some powder to make things complicated, to make things sort of exciting, but not necessarily systematic, and then guide you through, make your own way through this in order to make sense of it. Rather than me telling you, consider this in a systematic way, because the idea is to help you thinking rather than to give you my thinking. And I think there's a subjective manner to scientific thinking that depends on each of you, just a little bit like music of art. Everyone has his own angle to it. And I'd like to stimulate your own approach to things rather than to give you mine. So that's why I begin making a little bit of noise, so to say, trying to inspire that there's something interesting there to look at, but I don't start systematic. And then eventually I'll do the systematization so that hopefully at the end of this process, things will stick in a different way. Now, just to anticipate my style. Okay, so how do I introduce renormalization group theory? I'll do it, the best way that I know is dirty hands, hands on a problem. And you may immediately see what I mean without any blah, blah, blah. So we gonna look at the problem, give ourselves a goal, and try to solve that task. And by doing that, we'll discover that we need a fresh new approach to things and ultimately realize that this approach is called renormalization group. So the next two lectures will be based on what are on a set of lectures you can download from a webpage. They are from Peter Lapage. Lepage, one of the most inspireful set of lectures I've ever read. Very simple, yet full of concepts. And Peter is one of the most insightful scientists I've ever had the chance to take lectures from. And he's really providing you the essence of it. So I really recommend reading those lectures. They're called How to Renormalize the Schrödinger equation. You can download them from our webpage. So what is the question? What is the problem that we would like to start off with? And by doing that, we understand what the renormalization group is. I'll give you the following assignment. Suppose, the only thing that I will assume in this course, very much, is a little bit of statistical mechanics. I will claim what it is, and a little bit of quantum mechanics. You don't need to have taken quantum field theory. You don't need to have taken advanced quantum mechanics. Of course, if you have, good for you. It'd be an easier life, but you don't need to. Okay, so let's make this very clear. Okay, so our problem is the following. We have a physical system, a quantum system defined by a Hamiltonian. And to keep things as simple as possible, let's consider a physical system in 1D. So I have one bosonic particle in 1D with a potential. I mean, really, quantum mechanics 101. What do we know about the potential? Well, we know the long distance part. And we know it's basically a hydrogen atom. So let's say this is really a three-dimensional electron with a nitrogen atom, with a proton. But this is not exactly an hydrogen atom as we know. Maybe it's an alkaline atom, because there is, in addition to the standard Coulomb potential, there is a hardcore potential that describes the interaction at short distance. So in other words, what I'm trying to say is that my potential, if I were to graph it as a function of r, we know it falls off like minus 1 over r here. Let's say E is equal to 1. And we know that at some short distance, something else is going to happen. Maybe the potential is strong and attractive, or maybe it's strong and repulsive. I don't know. I don't want to tell you. As a matter of fact, I really don't know. And our goal, the only request is that the scale, let me call it A, the typical scale where this short distance potential decays, is much shorter than the typical scale where, say, the ground state of this system is. So, for instance, if this is really an atom, an electron, so m is the mass of the electron, you know that the typical size of an atom is the angstrom, 10 to the minus 10 meters. So we are assuming that A is much smaller than 10 to the minus 10 meters. Now, when you say much smaller for physics, it's really much smaller in your dream. And if you're lucky, if it's a factor 2 or 3, that's always the case for theoretical physics. So really, you know, let me start by telling the first general lesson that comes from already now, from this very first lecture. Physics starts when you can get two scales and build a ratio, and you can look at the regime. This ratio is much larger or much smaller than 1. So in this case, I have two scales. The Rydberg radius, that's typically 0.8 angstrom. That's the ground state of the hydrogen atom in the simplest form, right? And A is the typical scale where this unknown short distance interaction is. And we know that this is much less than 1. Whenever all the scales of your system are all in the same region and all these ratios are of order 1, that's where things become really complicated in theoretical physics, because no approximation can be done. And ultimately, the theoretical physicist's art is the art of making the right approximation, because if you don't make approximation, basically you have no problem to solve. even the hydrogen atom that, you know, our proud and joy, we can say we solved the hydrogen atom. No, you solved the hydrogen atom neglecting relativistic effects and magnetic effects. So you have made approximations because the, you know, typical velocity of the electron divided by the velocity of light was a ratio much less than 1. So everywhere in physics, everywhere you look at, literally everywhere, physics starts when you build ratio, dimensionless ratio, and you discover that some of these ratios are much smaller than 1. It's a very useful exercise to go back on your physics education, your favorite topic, and ask yourself the question, what is much smaller or much larger than 1 in this particular case? And you'll always discover, no exceptions, that whenever you're going to manage to make a prediction that can be checked experimentally, you have to have one of these conditions satisfied. I challenge you to find a theory that doesn't do that. Okay. So that's the only request we have. The hardcore of our interaction is characterized by a typical length. And this length is much smaller than the typical size of the systems we are interested in studying, in this case, the bound states of the electrons in this unknown potential. So what is our task? Our task, so our goal, let me write it somewhere here. Predict the spectrum, and possibly also the wave function you observe. So you see, what we are asking is really the impossible. We don't know the Hamiltonian, and we want to predict the properties of our system. So let me be a little bit more specific. We want to predict the spectrum and the wave function for distances of the order of the Rydberg. So for typical distances, therefore for distances much larger than the short distance where this unknown potential is localized. Okay, so if you think about this problem this way, it looks very much is very kind of corner problem for a niche of people who, you know, get, you know, freaked out about solving the Schrödinger equation if you don't know the potential. It doesn't look as profound, as ubiquitous, as fundamental as I advertised before, does it? Who cares about the problem of Schrödinger equation with an unknown short distance core? Why do you advertise this to be such a profound situation? And now I claim this problem is prototypical of what everyday physics is dealing, in particular, fundamental physics, but in general physics. Okay, let's erase the border. Think about for a moment. What are people at CERN doing at LHC? I don't know if, you know, all of you know what LHC is. I assume the physicists or people with a background in physics will know. Maybe some other people from QCB may not know. This is the biggest, the largest world particle accelerator, smashing protons of other protons, for instance, at incredible energies. And since the protons are very, 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 very large in momentum, then because of the uncertainty principle, you can use these to determine the structure of matter at a very, very, very small, very, very, very small scale. So really, particle accelerators are microscopes. Now, I'm bringing up something that has apparently nothing to do with the Schrödinger equation problem. But who can tell me what people are looking for at CERN right now? Any of you? Why are people still doing experiments at CERN? What are you trying to look for? Does anybody know? Anyone? You don't need to know. So if you know, good for you. You know, a few years ago, people were claiming they found the Higgs boson, right? You heard that. This was done at CERN, right? Yet that's not the reason people went to CERN and built the most expensive scientific enterprise humankind has ever built, far more expensive than going to the moon. The reason people built LHC is that they were looking for new physics. New physics, what does it mean? That people have, you know, by using previous infrastructures, previous accelerators, and before then, when people didn't have accelerators, they were using microscope, people were able to look into matter at smaller and smaller scales, right? And they discovered the atom in the beginning of the 20th century. And then later on in the 30s, they discovered the nucleus and the proton and the neutron. And then in the 50s, they discovered the pions. And then later on, they discovered the quarks. And they're going down in this Russian doll game of going inside. How were they discovering these new particles and new physics? By going higher in momentum, so that they could resolve smaller and smaller physics. So building larger and larger. And say the theory that we have today, for instance, is called the Standard Model. Some of you may have learned about it during their physical education. I don't assume you know anything of the Standard Model. All I need to tell you is that this model was obtained from experimental observation that was retrieved in the 70s and complemented with some additional inputs from the 80s, so to say. And it means that it corresponds to physical descriptions obtained with experiments that could reach energies or momentum as large, say, as 100 GeV, giga-electron volt. So if you believe Galileo, you have validated the theory. All the physics we know was validated. You know, for the physics to make sense, for that to be a science, you need to validate it experimentally. The fact that the equations fall up nicely and they fit means nothing if you don't have experiment. Now, since experiment was only valid up, say, to the 100 GeV, who knows what happens at the tera-electron volt or thousands of tera-electron volt scales. And in the past, the experience was anytime we were going to a next level of accelerators and next levels of experiment, we discovered new particles, new phenomena, new forces, and maybe relationship this force. So in other words, you should think yourself as a physicist is like a guy. Now you discover that I have a very bad drawing with a torch, and the torch can illuminate only until some distance. And here is dark. So although within the radius of your extension of your torch, you can see objects quite clearly, and you have it, you might develop the theory that you are in a corridor. You really don't know whether at the end, where it's dark, for some reason the corridor ends and you're in the middle of a forest, in something completely unexpected. So the dark place is the unknown. And that's where new physics sets in. That's the place where new physics is. So people build accelerators, or they look into cosmic rays, or they want to discover, to understand physics at the scale that is smaller and smaller and smaller and smaller. And that's the quest of physics, understanding how the universe works by going smaller and smaller and smaller, or by going larger and larger and larger, by changing scales. So really physics is really like changing your torch with another torch, they can shine light a little bit further, or behind you further, to largest distances or to shortest distances. Really is putting light into the dark. And the dark is where you have no understanding. And now comes the fact of life. No matter how large is your torch, no matter how good you've been for the last 3 centuries in developing physical theory, your torch will have a finite range. Maybe it's a super torch and it's 100 meters long, yet it's a finite range. No torch has an infinite range, meaning there is a maximum energy beyond which you have no understanding of physics. So really, if I'm now less pictorial and more quantitative, let me draw energies here. I don't know, the milli-electron volt. The milli-electron volt is typically, I'm starting from somewhere. I could go even lower, of course, but let's start from somewhere. Milli-electron volt is a typical scale for energies associated with thermal motions or molecular excitations in energy in macromolecules. Then, of course, you have the electron volts. That's where atomic physics. So this is molecular physics, if you want. The next scale, who tells me what's the next relevant scale for physics or new physics? Let's say, somebody. Do you have new physics at 10 electron volt? New particles? What is the next level of complicancy from atoms if you go microscopic? Anyone? I'm not going forward if I don't hear an answer. Any answer?
MEV.
Okay, corresponds to what? Physically right, it corresponds to what?
The mass of the electron.
Yeah, sure, right. But what do you discover if you have enough energy to have a mega electron volt? That the atoms, the nucleus of the atoms is actually composite, right? Because, yeah. and you discover nuclear physics. So the mega electron volt is nuclear physics, and then the giga electron volt is hadron physics. You discover that even the proton is not the point particle; it has structure, and so on and so forth, right? But at some point, say in a 10 on 100 tera electron volt today, let's say, hic sunt leones. We have no idea. Yeah, you can talk supersymmetry, you can talk strings, you can talk whatever you want. That is pure speculation if there is no data. And people have been proven wrong so many times that it should be pretty clear by now that until you have data, you don't have science. So above the largest scale where you can possibly test your theory, you have no idea. And to give an example, people built the LHC because by analyzing the theory they knew, they were pretty sure that new particles should have become evident at the tera electron volt scales. And they have a theoretical argument called supersymmetry that predicted that this new particle should pop up as soon as you pass, say, 10 electron volt. And they were so sure based on their theory that they convinced the founding agency to build LHC and found nothing. No sign of any particle at the 10 electron. So when you hear in the popular news, LHC was a fantastic success because they discovered the Higgs, you are hearing lies, and professionals in the fields know it. And I was working in high energy physics, so I know what I'm talking about. We all knew we have to give the news something to be happy to justify that we spent that money. But the money to build LHC was not spent to find the Higgs. We knew the Higgs was there. There were so many indirect proof. Just as much as we never saw a neutrino because the neutrino escapes but we know it's there. We knew the Higgs was there. What we were looking for was supersymmetry, and supersymmetry was not found. But you cannot tell the press, hey, look, we haven't found supersymmetry. We don't know what's beyond the 10 electron volt scale, but now we know it's above the 10 electron volt scale. Before we thought it was about the 100 giga electron volt scale. Now we simply know that there's nothing between 100 and 10 electron volt. No, you have to give the press the information. Hey, we discovered the Higgs. Great success. Spending money is a great thing. Okay? So the quest is the quest for new physics. And this is a fundamental quest that occurs of any scales. Even when you go to matter scales where you understand things, say you have the question of understanding things at a better level of accuracy. For instance, you're working in biophysics, you want to understand life from a perspective of atoms interacting with each other. Now, in this case, the atomic physics is the new physics, because if you look at the biologists, for them, when they draw whatever cartoon they draw, you have a ball. This ball is a protein, and this ball maybe attaches to a membrane, and they have this cartoon description. Then we are in the middle of a revolution where people are trying to give physical basis on this and discover that this protein is actually made of atoms interacting with atoms, and provide a more systematic understanding at a higher level of accuracy. So now, with all this big and long chit-chat discussion, we go back to our original discussion. Why is this fake hydrogen atom relevant to us? Well, simply because that's what we do all the time. All the time, we have some infrared physics we understand. Large distance physics I will call low energy. Large distance equals small momentum. Small momentum equals small kinetic energy. So if I want to study large distance, I can use slow probes. If I want to study short distance, I must use fast or highly energetic probes. So for me, I will refer to the long distance physics we understand as the infrared physics, although it has nothing to do with colors and electromagnetic radiation. It's just a nomenclature. And there's physics beyond the torch that I will call ultraviolet. And in physics, no matter what scale you choose, you're always in a condition that you understand the ultraviolet, you understand the infrared because you can make experiments here. But there's an energy beyond which you cannot make experiments, either because you cannot build an accelerators to go at that level, or because simply the technology doesn't allow you to. Again, let me give an example to biophysics. In biophysics, you would like to be able to understand the structure of a proton as it evolves in time with atomic resolution, but you cannot get just pictures of the proton evolving in time from experiments. You can get a picture of the global, perhaps, shape of the proton in terms of the electric charge, maybe the size. That's the low resolution information you would like. So you have infrared information, you would like ultraviolet information. But, so the problem we set up to discuss today is therefore the following one. We have some ultraviolet physics we don't understand, but we do understand infrared physics because we have plenty of experiments that tell us that the infrared potential is the Coulomb potential since the days of Coulomb. And given this situation, we want to make predictions and learn something about the system without being able to know experiment to infinite accuracy in distance. So without being able to push the experiment to arbitrarily large energy. Hey, this is what we do all the time. We never are able to push the experiment to infinite energy because experiments are machines, and machines need a power supply with a plug, and that plug needs energy. And if you don't have that energy, or you cannot control that energy, you will have a higher. So there will be a cutoff, natural cutoff. So all physical theories, ultimately, fundamental physics is about dealing with the situation that I depicted in this paradigmatic hydrogen atom problem. Are there questions so far? There are no questions. Let's give it a try. So the menu for the dinner will be the following. We'll try together to provide an answer to this question. And we'll do it in a most sensible way we can think of. I will guide you in trying to come up with an answer to this question. How do we predict the spectrum? It will be more or less phenomenological answer. Then we will discover that if we proceed this way, which looks fine at the very first sight, we run off a hard wall. We smash our nose on the brick wall, and we can go no further. There's a fundamental problem in the most sensible way we think we need to proceed. And then we'll discover what's going wrong, and we restart over based on this experience, and we will do things the right way, and we will be able to penetrate the wall. And this right way will be the renormalization group. Okay? So now you begin to see that whatever this famous renormalization group is something that allows me to penetrate the wall and shift the cutoff of my theory further, or if you want, to extend or modulate the distance that my torch can illuminate. So, enough talking. Let's give it a first try. So we know we have an interaction. So the first try the physicists historically have always done is to build a phenomenological model. Let's build a phenomenological model. And let me be very clear from the very beginning. Sometimes, especially in Italy, we have a formal education to physics. We associate phenomenological model to and correct model, rigorous model as, yeah. There's nothing wrong with a phenomenological model. Sometimes a phenomenological model, something you don't really understand, but you cook some ingredients just because you want to capture something. This is a fundamental first step to understand things. Later comes formalization. And the greatest discoveries have been made by those who didn't have a complete understanding of physics, but they were able to capture the right phenomenology with one of two terms. Build a simple back of the envelope model that sort of cracks the code. And once you've cracked the code, then you can build your favorite Lagrangian with all the mu's and u's and covariant and contravariant indices and get fun from math. And until you understand what's the missing ingredient, you're at your starting line. So let's move on from the starting line. Let's build our first phenomenological model. So how do we build a phenomenological model to compute the spectrum from this problem? Let me remind you, all we know is this part of the potential, and we know there is something here in the ultraviolet region which is short range. So I have a Hamiltonian, I have my 1 over r, let me send e to 1 from this point 1, and h bar to 1 for simplicity. And then I have my hardcore potential. So how would you model this hardcore potential? Can anyone tell me something? I want from you, let's pretend we are a research team. And I am coming to you and say, guys, we need to solve this problem. I have experimental friends who can measure the spectrum of this system. They want to know the spectrum, they can test it, right? And you know what? Let's play a game. I have written the code, actually not me, Lapage has written the code, but I have also have one in my own folder, where I chosen a potential here. Attractive or repulsive, doesn't matter. It's written in the code. So when I ask the code to compute the spectrum, the code will give me a spectrum. So the code will play the role of nature. Nature knows what's the ultraviolet physics. We don't, but nature knows. So anytime we interrogate nature, we make an experiment, we get an answer. And if you do things right, we get the right answer. So for us, the answer would be the data of the spectrum that the code provides. it's not an experiment because it's a code, synthetic code producing synthetic data. But let's pretend those are not synthetic data. They are real experimental data for this fake system we're discussing. Is this clear to everyone? So the code that produces the spectrum is a fake experiment. And since nature doesn't tell you what is the ultraviolet physics, I will not tell you what's the hard code, and you will never know. Okay? So, but we know it's there. And our goal is to build a theory that explains the spectrum and possibly is predictive. So maybe you will use a couple of points to fit the data, but you want to predict the next point, and you can test whether you're right or wrong by looking at the data that our code returns to us. So you know, I can give you the data of the code, but let's, you know, I'll disclose this data later on during this next lecture. But you know, there are just a few energy levels. And I'm asking you, how do you start making sense of this data? What would you model? How do you build a phenomenological model for this? Anybody? What does my team say? Be creative. Any idea? Is the problem clear?
Maybe starting with some Dirac delta.
Very
or,
good. Very right.
Mere the function.
Absolutely.
Probably.
That's a good point. So it's a short range. Any function that is short range should work, right? But maybe the delta function is the simplest because I know how to evaluate integrals with a delta function by definition. So let me start saying this is a constant. Tell me a delta function of R. It's a model. Why is it a model? Well, because I have no idea whether the potential is a delta function. Actually, I can tell you it's certainly not a delta function because the delta function is not a function. It is the limit of a function when the smearedness of the function goes to 0, or technically speaking, it's a distribution. So certainly it's not going to be a delta function, but let's pretend. Okay? And let's assume, just for the sake, so is everybody with me in this? Does anybody agree on that? So this corresponds to saying, basically, a model in which the potential does something like this. Right? Or the other way around. I don't know the sign of the delta function until I interrogate the experiment, because this is an unknown coefficient, right? Fine. So I will also make, so let's interrogate the system. So what I will plot here I will interrogate this to interrogate the system. I will use this following plot. On the x-axis is the principal quantum number. So the n, you know, if you remember the hydrogen atom theory, you have r, theta, and phi. Then you go to spherical harmonics, right? So now I will stick only, for sake of simplicity, you can complicate this at taste. There is no need to add useless complications. So let's stick to S wave. Suppose we're only interested in the experimental spectrum in the S wave channel, which means that we set L to 0. And so we can basically neglect all the angular behavior. I only have S waves. Then all my physical theory is determined by the radial component of the wave function, spherically symmetric as a function of R, and n is the principal quantum number. So I have a 1, 2, 3, 4, but rather than plotting it this way, here I am going to plot it the opposite way, 1 over n. Why? Because I want that, you know, as I go to the right, I'm going to near to the continuum threshold. And these are the lowest energy states, because you see, this is the zero energy state. These are a few weakly bound states, and eventually this is the ground state. But in the perspective that I'm given, this is a large energy difference, and this is a short energy difference. And I consider this the low energy state. Why? Because if you remember, when you go high in the principal quantum number, the mean square radius grows, right? So your system becomes larger and larger and larger. The wave function becomes more and more delocalized. And so, you know, large distance, small momentum, the system becomes large. And so in this discussion, the analogy with the, you know, the torch, the high energy physics, the infrared sector holds if this is the infrared sector and this is the ultraviolet sector. Even though the ground state people think about it in terms of the lowest possible energy, but really here the lowest possible energy is referred to the continuum threshold, 0. So these are my low energy states in this discussion, okay? So I want to approach the lowest energy state as I go here. So I got 1, 1/2, 1/4, and so on, or 1/3, whatever it is. And so here is high energy. And here on the y-axis is the difference between the experimental value of the energy for the corresponding states and the energy that I predict in a given model. How do I do? I take my Hamiltonian, I solve it, get the spectrum, take the difference between the real value of the corresponding states that my codes give me, which is the same thing as nature. And by this difference, I get delta E, and divide by, say, the value that the experiment gives me, the relative error I'm making in my theory. So the first thing we want to do is how important is this term at all? So basically what I'm saying is that, okay, the scale is not very nice here. So I get 1, 1/2, 1/3, and so on and so forth. So basically what I'm discovering is that as I go up, as I move closer to the, okay, fine, sorry. Again, if I plot it this way, sorry for the mistake. I'm running out of stamina. When I go, let me replot it in a normal way. So I get 1, 2, this is the ground state, and this is the high excited state. And when you use, one moment, I got lost for a second. Hold on, let me check my notes to make sure you're not doing stupid things. Because I want to use the same plot that is done in the theory, in the lectures, not use my own plotting. I just want to make sure. Okay, fine. Yeah, I was correct as I was doing before, right. So here are the low energy states. And here are the ground state. So what you discover is that the relative error you're making, if you only keep the Coulomb term, rapidly becomes of order 1. So let's use a logarithmic scale as you go closer and closer to the ground state. So that's this red curve is the result of comparing the hydrogen atom energy levels. Of course, you have only points because you have only a discrete set of principal quantum numbers. So let me draw it as points, really. You compute the hydrogen atom quantum numbers. You neglect the hardcore altogether. you take away the exact value that my code gives me and divide by the exact value of my code. You get a relative error you make if you close your eyes to the core. And you discover that you do pretty well for large energy scale, for states that are very close to zero in energy. But as you get closer to the ground state, you make an error of order 1. Which means that, you know, already by doing this comparison, we learn quite a huge amount of information, because you see, this comparison already tells me that this is a hard core. How do I know? Well, because, you know, physical intuition tells me when I get close to the ground state, the wave function gets smaller and smaller. I spend more time near the center, and I make an error that all of a sudden becomes very large, because this is a logarithmic plot, which means that this linear worsening of the prediction is actually an exponential worsening in prediction on a linear scale. So that means that as I go to lower, larger and larger energy, so I go closer to the ground state, I make an exponentially large error, which means that all of a sudden something got very bad wrong, which means I'm missing information, which tells me this is not a hydrogen atom, because if this was basically an hydrogen atom, I would have gotten a very low number all the way through here. The code is not giving me the spectrum of the hydrogen atom. But since I'm making very little error at large energy, it means that the physics that I'm missing is ultraviolet physics. There's some unknown short distance physics. That's why my data go wrong at short distance. And in the next lecture, Thursday, we'll begin by see how good do I get by building these phenomenological models. And in doing so, we'll discover whether we can do things better and maybe, you know, get some data that remain closer for longer. Okay? And making smaller error. I will we'll repeat these arguments next week, next lectures when we start. I'd like to close this lecture by asking you one thing. Please, I would like to set up a Telegram chat for this course. It's completely voluntary, but it has proven very effective in the past. Because in principle, there's the Moodle platform for communicating. But people don't always log into the Moodle platform. Whenever we have something very urgent to communicate, maybe I'm sick, maybe my kid is sick, maybe for some reason the lecture must be postponed, or I don't know. If you have a Telegram chat, I can communicate to the students. Of course, for a privacy reason, you're not requested to do that. So whatever there is news, I will put it also on the Moodle platform. So you're not supposed to give me your phone number or to set up to be part of the to the Telegram chat if you don't want to. Let me be very, very clear. It's something I do it for the students, giving my own phone numbers. We don't feel forced to do. So I'd like some of you in the next day, maybe, to set up a Telegram page. I will give my own number in the chat here, and maybe somebody will take care of setting up a page, collecting the numbers. Okay, can somebody take charge of that?
Okay, yes.
Okay, so are there questions to what we did so far? We will go over from here and repeat what we've done today again a little bit before going on next lecture. Well, if not, you can save your questions for next time. Thank you very much for being here in this first lecture. We'll see how things will go later on in the course. And then after this introduction to renormalization group theory, which is very low level in terms of mathematics, we will start building more mathematics by going to functional integrals and path integrals and all these tools, and eventually stochastic dynamics and statistical fields. So those of you who are more theoretically inclined, don't you worry, you get your fair share of complicated math. But I want to root that math into physics first and not vice versa. Try to get out physics from complicated math that was introduced for the sake of having complicated math on the board. Okay? See you Thursday.
Goodbye.
Thank you. Bye.